In this video, what I would like to do is figure out the equations of motion for my mass M1 and my mass M2. So I have two blocks here, and I'm going to refer to them as M1 and M2, but I have this block which has a mass of M1, this block which has a mass of M2. Between these two masses, I have a spring, which a spring constant K2. Between M1 and the wall, I have a spring constant of K1. And between M2 and the wall, I have a spring constant of K3. Now, I'm told that my springs are initially unstretched, and I'm going to be moving my entire system to the right. So M1 and M2 are both going to be moving to the right. Now, we are not told whether M1 is moving further than M2 or M2 is moving faster and further than M1. But I'm going to show you, I'm going to do it both ways. It doesn't matter as long as we are consistent with the assumptions throughout the problem. Now, let's first go through this problem and assume that M1 is moving further than M2. In this case, and for right now, I'm just going to ignore these two springs when I'm talking about this, because we know that regardless, K1, when we do our problem, K1 is always going to be stretching. K3 is always going to be compressing. So when we're trying to figure out what's happening with K2, at least trying to understand it mentally, we can sort of ignore K1 and K3 just to understand what's happening with K2. When we put it to our equation, yes, we of course will need K1 and K3 to come back in. So let's start by thinking of it like this. If here's my mass M1, it's connected with a spring to M2, let's assume, or let's think, if what happens if they are both moving in this direction at the same speed. So let's just say like 2 meters per second. Well, if this spring was initially unstretched and we're both moving at the same speed, we're just translating. And in that case, my spring's going to remain unstretched. But now let's say M1 is moving at 3 meters per second. And again, these numbers don't mean anything, but it's moving faster than M2. So when that happens, that means I'm going to be compressing this spring because M1 is going to be running into M2. So if I compress this spring, and I gotta draw these two boxes again, but if I compress the spring, what happens with my force? Well, the spring is going to want to push back to get to its unstretched length. So it's going to want to push back this way, and it's going to want to push back this way. Now, the force, remember our spring force, is going to be equal to K times delta X, where K is my spring constant. Delta X is the distance that the spring has been compressed or stretched, is going to be K2. And this compression, this distance, is going to be some distance x1 minus x2. And let me put this as M2. Now we can go back and we can do we can put in what's happening with this spring K1. So this spring with the spring constant K1, it's always being stretched. So it's always going to want to pull back this way to get rid of that stretch. And that's going to be K1 times X1. And this one right here, K3, is always being compressed. So it's always going to want to oppose that compression. And it's going to have a force of K3 X2. Now, like I said, I want equations of motion for each of these blocks. So we're going to start with M1. We do the sum of my forces is going to be equal to mass 1 times whatever its acceleration is, x1. We'll say to the right is positive. So I'm going to have minus k1 x1 and then minus k2 x1 minus x2. That's all I have for M1 is equal to M1 x1 double dot, so the acceleration of 1. When I do the same thing for M2, So M2 is going to be right here. I have the same equation. Sum of my forces are equal to my mass times my acceleration of M2. So again, we also have positive is this way. So I'll have K2 times x1 minus x2 is going to be minus K3 times x2 is going to be equal to m2 times the acceleration of my second block. Now, let's just go through and distribute this negative sign right here. So minus K1 x1 minus K2 x1 plus K2 x2. And I'm just going to write it on this other side right here. So M1 x1 double dot is equal to that. Likewise, over here, I'll have M2 x2 double dot is equal to K2 x1 minus K2 x2 minus K3 x2. And these are my two equations of motion. I'm going to box them so I don't lose them. But I'm going to do the problem again. And instead of M1 moving further than M2, I'm going to say, okay, what happens now if M2 moves faster and further than M1? Well, first I need a new free body diagram. So here's M1. Here's M2. Now in this case, what's happening? Again, let's put those numbers to it. Let's say that M2 is now moving at, say, 3 meters per second. M1 is moving at 2 meters per second. So what's happening? This is moving further away, faster than M1. So that means my spring is going to stretch. These numbers don't mean anything, but so if my spring is going to stretch, and my spring is stretching this way, that means that it's going to want to come back this way and come back to its unstretched length. Same with this. And here I have K2. Now, how far has the spring stretched? Well, it's going to be this x2 minus x1. You can see right now these are opposite. We also know that this doesn't switch. Like we said, it's always going to be stretched. This one also doesn't switch. It's always going to be in compression. So now let's do my two masses again. So here, M1, if I sum my forces, it's equal to my mass times my acceleration of 1. Well, now I have minus K1 x1. I'm going to have plus K2 x2 minus x1 is equal to M1 times its acceleration, x1 double dot. Now let's look at mass 2. So the sum of my forces is equal to my mass times its acceleration, M2, x2 double dot. Okay, so now we're going to have minus K2 x2 minus x1 minus K3 x2 is equal to M2 x2 double dot. Again, let's go through and let's distribute this K2. So minus K1 x1 plus K2 x2 minus K2 x1, and again we'll do M1 x1 double dot is equal to that. Now on this we'll do again M2 x2 double dot, so we're just switching the way we're looking at the equation. So this is going to be minus K2 x2 plus K2 x1 minus K3 x2, and this is my equation of motion. Now, if I did everything correctly with my signs, these two equations should be exactly the same as these equations. So m1 x double dot is equal to, here we go. So minus k1 x1 minus k1 x1 plus k2 x2 plus k2 x2 minus k2 x1 minus k2 x1. So this one's the same. We did it correctly. Now here, m2 x2 double dot is equal to, all right, minus k2 x2 minus k2 x2 plus k2 x1 minus k3 x2 minus k3 x2. So what I've shown is, as long as you make your assumptions and you are consistent throughout, so when you have these two masses or these two particles or whatever, you can't assume it's going to, you can't say, okay, we're going to go this way and this way. You have to have consistent assumptions throughout the problem, and you will get the same answer. Now, the one issue that some students run into is they will make those one assumption for one block, another set of assumptions for the other block, and then the equations won't work out.